Hello all, welcome to part two. We're going to be classifying systems of equations. And when we have systems of equations, we have three different types. We have we have consistent independent, and we have consistent dependent. For inconsistent, the graph is two parallel lines. So they never cross. And this is an inconsistent system because all systems should have a solution. Okay, so these are parallel lines. These aren't great parallel lines. But understand that the graph is parallel lines. And I made a spelling error. Should be two L's, EL. So parallel. So for it to be inconsistent, it has to be parallel lines. And since they never cross, there's going to be no solution. The graph for consistent independent is two lines that intersect. And you have an actual solution point. Two intersecting lines. Get your handwriting together, McAllister. Two intersecting lines, and it has one unique solution. Which would be the ordered pair. So we'll put x comma y. And consistent dependent is just one line, when the equations make the same line. And this is all real numbers. Not real hashtags, real numbers. And the answer, the solution, is going to be an equation in slope-intercept form. Okay, now that we have this foundation established, let's go look at a couple of examples. Alright, in the first box, I've got two lines. I've got 1/3 x and 1/3 x plus 1. Notice that they have the same slope, but different intercepts. Well, this means that they are parallel lines. See that they're parallel? So these are inconsistent. And since they're parallel, they're never going to cross each other, so they have no solution. Let's look at this example. I have negative x minus 3 and negative 1/2 x minus 2. So here's 1/2 x minus 3 and negative x minus 3, negative 1/2 x minus 2. And they cross right in here. That's the point they cross at. So that's going to be negative 2, 1. So it's consistent independent because the lines work independent of each other. And the unique solution is at the point negative 2, comma negative 1. So I get this ordered pair from this point here. That's my solution. Alright, and then lastly, I have y equals negative 3x plus 1 and 3x plus y equals 1. Well, notice that there's only one line. See, they've labeled line 1 and line 2 to be the same line. This means that the lines are not independent of each other. They're actually the exact same equation. Okay, if I solved it for y, or if I added this over, it's the same equation, which means that they have infinitely many solutions. Alright guys, so just make sure you look at the lines properly on the graphs, identify the solution, or identify the system type, and then identify the solution type. Let's look at one more example. Alright, here we go. I've got three different graphs, so let's look and see which ones they line up to be. In the first one, line 1 right here, line 1, L1, is 1 half x minus 3. So from negative 3 goes up 1 over 2. And the second one's 1 half x minus 1. So from negative 1 it goes up 1 over 2. So these are parallel lines, which means they are inconsistent. They're inconsistent because they don't match they do not match the requirements for being a regular system. So that means that there's no solution. Not that they're not a regular system, but we want our systems to have a solution point. Line 1 and 2 look like they're going to work out to be the same line. Here's line 1, here's line 2, and they are the same. So they are dependent because they are the exact same, and all of their solutions depend on each other. So this means that they have infinitely many solutions. Every point on that line is a solution. And here we have two lines that intersect right here at this point. So this is my solution. And since they do in fact intersect, they are consistent independent. Their lines are independent of each other. So that means there's a unique solution, and that is at 1, negative 1. Alright guys, just remember to make sure you match up the consistent dependent, and consistent independent correctly and get the solution types correct. You can always use the chart at the top of the page. Good luck.